All right, everybody, I wanted to talk to you guys about your experiment number 3 or your online experiment number 3. This is an experiment all about oxidation and reduction, and I wanted to give you a little bit of a rundown or a discussion of what oxidation reduction consists of. Now, when it comes to oxidation reduction, it's important to understand the terms themselves. Okay, so oxidation is the process by which an electron is going to lose an atom is going to lose an electron. So one of the ways that people look at these different things or look at these terms is they'll use a mnemonic in order to memorize it or to learn it. So a common mnemonic is oil rig, and that means oxidation is loss of electrons, and then the rig is reduction is gain of electrons. Okay, so a way that that is illustrated is commonly we'll look at a metal. For instance, the metal lithium. Okay, so let's think about what lithium looks like on an atomic level. Lithium has a couple of different subatomic particles. Lithium has an atomic number of, my cursor is messing up here. Oopsies. Lithium has an atomic number of 3. Sorry about that. Li has an atomic number of 3, which means that it has 3 protons. It has a mass number of 7. Again, there we go. Mass number of about 7. So that means it has a number of protons and neutrons. So 3, I already talked about 3 protons. And 4 neutrons. What we really care about when it comes to oxidation reduction is we only care about the number of protons and electrons, because we know that lithium, as long as we're talking about lithium as a solid, we're saying Li solid has a 0 charge, means it has 3 protons and 3 electrons. Those basically cancel one another out. Okay, now what oxidation is going to look like for lithium is Li solid gets oxidized, and whenever it gets oxidized, it breaks down to lose a single electron. So it's going to lose an electron. Therefore, lithium still has 3 protons, but it only has 2 electrons. So now that means lithium has an imbalance in its charge, and it's going to have, I'm going to put AQ as my the state of this, but it's going to have a charge of +1. So whenever you talk about a group 1 metal or a group 2 metal generally being +1 or +2 respectively, that's where that number is coming from. Now, something getting reduced. So this is oxidation. Now let's say we have something like magnesium. Let's say that we've got magnesium ions. It's aqueous. If we add 2 electrons to this, we're going to make something like magnesium solid with a 0 charge, because it previously had a 2+ charge. We added 2 negatives to it. Now it has a 0 charge. So now what we have is a solid magnesium. What this means is that these magnesium ions underwent reduction. So you could say that those magnesium ions were reduced. So this procedure that we're going to be doing is all about what's getting oxidized and what's getting reduced. And we're looking at these different metals in solution, and we're going to ultimately come up with a metal reactivity series. So we can rank different metals based on their ease or difficulty of becoming oxidized or getting reduced. All right, well, thank you very much. All right, everybody, I wanted to go ahead and walk you through the first few parts of this experiment and give you an idea of what we're kind of looking for. Okay, so this experiment is all about oxidation reduction. Now, I've got it pulled up to chemcollective.org/vlab/106, and this experiment is all about oxidation reduction. What we're trying to do is we're trying to rank a series of metals based on how easily oxidized they are. Okay, so what we're going to do first is I'm going to go to my stockroom and I'm going to get, under solutions, I'm going to get 5 copper nitrate solutions. Now, one thing that's kind of cool about this is this shows that our copper nitrate solution is slightly blue. So that's not a mistake. Copper nitrate is a bluish green solution, and copper containing compounds are generally blue solids or blue liquids or blue solutions, I'm sorry. So what we have here is an aqueous solution of 0.1 molar copper nitrate, okay? Now, after that, we need to go back to the stockroom and now go to solids and get silver, get some copper, get some zinc, get some lead, and get some magnesium. Okay, so now here are the 5 different metals that we have on our bench. At this point in time, you need to take a picture of your lab bench to show that you have all of those different materials. What I'm going to do to keep my lab bench a little bit organized is I'm going to move each of my metals over by one of the Erlenmeyer flasks. Now my workbench is going to be a little bit crowded, so I want to, do my best to keep it somewhat organized. But the first thing that I'm going to do is I'm going to move my copper nitrate next to my silver solution. Silver is, or Ag is silver. I'm going to hover my silver solution over my copper nitrate, and I'm going to transfer a total of 10 grams. Now, this has the function where you can just select the mass and say pour, okay? And so I poured 10 grams into there. I poured 10 grams of silver into here. Okay, so now what this shows me is that I have a Erlenmeyer flask with a solution that's 25 degrees Celsius. I have a total of 10 grams of silver in there. I have 5.88 times 10 to the negative 14th solid copper atoms. I have a very small 3.70529 times 10 to the negative 14th silver ions. The vast majority of my silver, though, is in a solid form. Okay. Now, what I noticed here was that my solution did not change temperature. It was 25 degrees. And so what I would ask you is there much of a reaction at all here between silver and copper? Did silver go from Ag to Ag plus? Did it get oxidized? Well, I've got 10 grams of silver in there, so that suggests that no, indeed, this did not get oxidized. Okay. Now, I would say that silver is not easily oxidized by this copper nitrate solution. Now what I want to do is compare it. And this has you go through all 5 of these different metals. What I'm going to do is I'm going to add zinc to a copper nitrate solution. Again, 10 grams, pour. Oh, look at that. The temperature of my solution went up to, we're at 20, I saw 29.04 grams, or 24.09 degrees Celsius. So that suggests that zinc is oxidized by copper. One thing that I notice whenever I look at, and I'm going to try to use my annotate function here. When I look right here, I can see that the zinc that was in my solution and the copper that was in my solution, well, the zinc that I added, some of it went away. And what arrived, or what appeared new, were these Zn2+ ions. So zinc was indeed oxidized by copper, okay? So I have 2 data points that basically support that zinc is reactive with copper. Now, what I'm going to use as my barometer for whether or not a metal is oxidized and how easily oxidized it is by this copper solution is I'm going to look at the temperature. And I can tell you right now that zinc, well, zinc is easily oxidized by copper, and it's more easily oxidized than silver because of the fact that I saw my temperature go from 25 degrees to about 29 degrees. Now I'm going to do one last one. I'm not going to do all 5, but I'm going to do one last one. Oh, and before I proceed, look at this copper solution, my copper nitrate solution that I added zinc to, compared to the copper nitrate solution that I added the silver to. Well, the copper nitrate solution that I added zinc to, well, now it's white compared to the copper nitrate solution that I added silver to, which remains blue. So that color is an indicator that a reaction did take place. Okay, so now the last metal I'm going to use is magnesium. Okay, so I've got a temperature change of 0 degrees from the silver, of about 4 degrees from the zinc. Now I'm going to add magnesium to this copper nitrate solution. Again, 10 grams. Oh, nearly 38 degrees. And it's going to go down. It's going down slowly but surely. But my magnesium reacted with this copper solution and it shot way up. So my temperature difference there is basically an indicator of reactivity. So magnesium reacts more violently, I guess you could say, based on temperature alone, than the zinc does. So we've got magnesium is more easily oxidized than zinc, which is more easily oxidized than copper. And all of these are through the comparison to basically what copper does to them. Okay, so I hope this was helpful. And you're going to go through and repeat all of this and rank all of your different metals based on how they react with these different solutions. And the good thing is, well, there's very little chance of any sort of chemical burn or anything like that. That was a dumb joke. Anyway, the good thing about this is you could do this over and over and over again. And heck, if you wanted to, you could say, well, I want to throw 50 grams of lead to see if anything is different than 10 grams. Okay, 50 grams. Well, that caused it to go up to 10 degrees Celsius. And does that, you could do it again and do it with 10 grams or something. But each time you're going to take all the necessary pictures, you're going to clear your workbench after each time. And at any rate, I hope this is helpful. And what this is really supposed to illustrate is how different metals react with one another, or how metals react with ions in solution. So I'm going to revisit that in just a second. So we just walked through the procedure and what it consists of making these different solutions. I'd like to show you what this kind of looks like on a, I guess it'd be more like a theoretical or, sorts of practice problems that you might see. So and the concept behind this experiment. So what we have is, I'm going to go ahead and start with there we go. Let's go ahead and start with zinc. And there's my cursor, and it's being problematic. This is frustrating. Okay, so let's go ahead and let's start with that copper nitrate solution. We have Zn solid plus Cu NO3 2. And that is aqueous. So since that's aqueous, it's important to know what we have going on there. Well, we don't really have those copper nitrate molecules kind of packed together. What we have is something that looks a little bit more like this, where we've got Cu, we've got Cu 2 plus AQ plus, I'm going to put the 2 out in front of here, 2NO3 minus AQ. So that copper nitrate dissociates into one copper ion and a pair of nitrate ions. Now we're going to combine that with Zn solid. So when you think about what's happening here, you've got that zinc atom, one zinc atom, or those 10 grams of zinc atoms. And they're going to come in contact with the copper ions and the nitrate ions. Now, the question is, what's happening? Well, on the other side of this, one of the things that's happening is we're getting Zn plus. We're also getting Cu, well, solid. Okay. Now, I'm not going to work to balance this entire reaction or anything like that, but let's think about this in terms of each species. So the nitrate ions remain in that solution. What we care about are the zinc atoms and the copper ions. Then we also care about, I'm going to put AQ down here, we also care about the zinc ions and the copper atoms. Okay, so zinc here is going to go into B, not very good at drawing lines, to the zinc ions. On the opposite end, or the other party here, is these copper ions, which end up as copper atoms. Okay, so in order to do that, what's happening? Well, Zn, solid, is going to Zn plus an electron. So Zn is being oxidized. Now Cu2 plus, well, Cu2 plus has to add 2 electrons to make Cu S Q. Therefore, what's happening to the Cu2 plus ions? These, going to that, are getting reduced. So when one thing is being oxidized, it's giving up electrons, and therefore, well, where are they going? Are those electrons just going off into the ether? No, they're going to another species. And they're going to those copper ions, in which case that copper ion is going to collect 2 electrons and turn into a solid copper atom. So this isn't a balanced chemical reaction. We're not worrying about balancing a chemical reaction right now, or this electrochemical reaction right here. What instead we're looking at is which species is being oxidized, which species is being reduced. And so now what you have, and as you go through this procedure, you'll be able to look at the different metals and determine which one is being most easily oxidized, which the one that's most easily oxidized is producing the most heat. Which one is most easily being reduced? Well, if it's being reduced, or sorry, if it's being easily oxidized, then the opposite is true. So if the thing that is most easily oxidized is the thing that is most difficult to reduce. The thing that is most easily reduced is the most difficult thing to oxidize. All right, so I hope this helps out with this online experiment. You know, this isn't obviously a perfect alternative to the lab, but it gives you the opportunity to play around with different solutions, look at those solutions and look at those metals and how they react with one another, see the heat that's generated and everything like that. All right, well, I hope this is very helpful. There are some office hours posted on your Canvas page. If you have any questions, please feel free to email me or Dr. Holland, and we'll try to jump on and help you out. All right, well, thank you very much. Goodbye.